projectile motion? No.
No, no.
Just the dropping.
Yeah. Next week is projectile motion. That's important.
Hi.
Very good.
So you didn't see anything today, right? Even the previous sample, I thought you saw something, right?
I sent you the text file,
Yeah.
and I mean, I don't know where that graphene peak is coming from if it's not showing up again now. So, yeah, I don't know. I'm a little confused.
This is the sample you showed me, like 500 and some.
Yeah.
So now you don't see any of those?
Mhm.
That's very strange. So every time do you look at the silicon wafer to make sure your Raman is giving right?
Not every time, but
You have to do
I
every
have
time.
done, yeah.
Every time we have to make sure if you are missing something.
Maybe.
Yeah. Just keep that sample, I want to check that.
Sure, no problem.
Yeah. He's from the moment he's using the Raman right now.
Okay.
Yeah, he wants to do something. Right.
How are you?
Good. What's up, Jacob? You been studying for this weekend?
I've been playing catch up.
Catch up a little bit?
Yeah.
They were doing qualifying exam in the weekend.
Yeah, so it's like, oh, I have all these homeworks I need to catch up on. It doesn't make me feel any better if I study and not do this. So.
In the qualifying exam, professor, like if all the steps are correct and if the last answer is wrong, I mean if an addition has gone wrong, like do they cut like
You might lose 1 point, yeah.
it was like I added 203 to 100 with the exact thing, fraction.
Who cares about that? If you have the procedure correct, that's all. Nobody cares about final answer. Unless we ask you to prove that.
Okay, that is fine.
But this time, I think the mechanics problems were both like the basic questions, right?
Chandra.
Yeah. So you two guys, I just talked to the other people, so you know what topic you are going to talk about.
I have not decided yet.
I need to know before.
Okay.
Just let me know before next class.
Okay.
So same with you.
Same with you.
Yes, I don't want 2 people to follow the same topic.
Yeah.
Also, it has to be something that we learn from this class. Okay, so last time we talked about this scanning. So these are the 2 things I'm going to quickly talk about. So and get back to the spectroscopy. So these are something called this probe microscopy, right? So you have some kind of probe to do the imaging. So this is first thing is the scanning tunneling microscope. So this is nice thing is this is based on something that we all know, the quantum tunneling technique, right? So here what we have is basically the sample you are going to image. Then we have very sharp tip. So I'll show how to make that tip. But the problem is both the sample and the tip have to be metallic. So that means have to have enough free electrons, right? So when you have the free electrons, then your wave functions in quantum mechanics, you have each electron from this surface and each electron from the tip. So you have the quantum wave function, right? They are going to kind of overlap. So then you can have some tunneling through that gap, right? So then the way it works is you have a small current through here. So these are typically in picoamperes or nanoamperes. So then this is a piezoelectric scanner here. So that will make your probe move up and down. So that's how it's going to image, right? If you have atoms like this, right? So basically, so when it is moving up here, so it's going to probe the atom. So then if it is going to go down, so if you have some surface like this, right? So then probe is here, then when it goes here, it's going to go down. So then the feedback mechanism here, so that will keep the current constant. So that's how it is working. This is something called the negative feedback, right? If something happened this way, the feedback will provide the signal to go in other way. So that way you can keep the current constant. So then you can image how this tip is moving up and down, right? That can image the tip. So that's why this the XYZ, the piezoelectric device is so important. Just remember, the whole idea is just keep the current constant by using this feedback, is a negative feedback. So these are the things you need in this STM. First you need to have a very sharp tip. So typically you can use a tungsten wire. Then you can either make some nice cuts. So take a scissors and make just one from one side, then another one, just do like that. So you have to practice that. Or you can put it in some etching solution and apply some potential between another electrode. So then you have some electrochemical etching, right? So then you have to make sure that is during etching that is moving above the liquid surface. So that way you can make a really clean tip. So then there are some others, like the piezoelectric scan is very important. So because that's, you need to have something called this piezoelectric coefficient and all these things you need to know. How much per typical piezoelectric, what you need to know is how much is going to elongate, right, or compress for a given voltage. That's what the piezoelectric means, right? By applying voltage, you can make it shrink or expand, or by doing this one, you can produce voltage, right? That's the piezoelectricity means. So you need to know that you need to have something like some volts per angstrom, right? So that's kind of a number you need to know. Then another thing is this vibrational damping. That's very important. If you have a, just imagine you have this one probing, right? You have surface, then this one is probing. You are looking at this moving. So just if you keep it on any table like this one, we know any object has its own resonant frequency, right? So any objects are typically, they are moving at very low frequencies, right? So if you have that frequency, definitely that frequency might be even larger than your this displacement, right? So that means you need to really isolate all the vibrations. So that's very important. There are like tables you can buy, they have vibration-free tables. That means you have to have some air fill some legs, right, from that, so that will damp the oscillations. And also you can use some kind of springs. So that's damping, right? So we all know the damped oscillations, right? So if you have some oscillation, so typically if you have simple mx double dot equals minus k, you have simple harmonic oscillator, right? But if you have some kind of damping force, right? So then we know it is typically it's going to, and eventually you have the critical damping, and eventually it is going to. This is what we need, right? We shouldn't have any vibrations. So that's very important, this vibrational damping. So most of the time people have even rubber band to kind of suspend the scanning tunneling microscope. That way you don't get the, if you put on a table, this is really bad. So even things like fan, so those vibrations are in very low hertz, right? 1, 2, 3 kind of hertz, so they can easily interact with these things. So vibrational isolation is very important, not only STM, even AFM and all these things. So then we know the feedback mechanism. So yeah, this I just read this one. Everything happens just simple quantum tunneling, right? You have the sample, then you have tip. So this is your sample, the metal 1. This is your metal 2, right? So then you can write your wave function for this one, wave function this one. So then you have some your potential barrier, right? So you have to overcome that barrier for these electrons to move from here to here. That's the tunneling, right? So that's the current we are measuring, tunneling current. So if I represent my sample, say this one, so that's a metal. That means your electron can be filled up to the Fermi energy, right? For metals. So then the other side you have the tip. Tip is also metal. That also has a work function, right? We know, everybody familiar with the work function? So typically, if you have something, if you write the energy, so all the electrons in a metal, they are filled up to Fermi energy, right? So typically density of state above this one is 0, here is 1, right? So, but we know typically at any temperature you have some electron moving to this side. That means something called the Fermi-Dirac distribution is not exactly 1. You can have some electron coming here, right? And some losing from this side. So, but at 0 Kelvin, it's pretty much like this, right? Those are details. So only thing we need to know is up to this Fermi energy, you have all the states filled, right? So you have filled state here and all the unoccupied state above here, right? So then we have something called the vacuum level. Vacuum level is here still your electrons are in the material, right? But if you can have enough energy, this electron can come out of your surface, right? That's what we say it is going to the vacuum level. That means you need to provide enough energy to overcome that barrier. So this is we call the work function, right? So work function is what you need to remove the electrons from your surface. So that's what here I am drawing. You have sample, this is your Fermi energy. So that has a work function phi 1. This is tip, it has Fermi energy 2 and the work function phi 2. Now if you bring these two together and if I apply some voltage, we know this is going to bend, right? Because we have electric field is given by delta V by delta X. That means your V is something like E times delta X, right? So linear, you can see how this one. Now this, if you draw this one in different way, it's more like having potential barrier. But if you have enough energy, they can tunnel through here because you can find some allowed states. This side, it can move to the other side. So that's what we are looking at from the scanning tunneling microscope. So everybody know how to write the Schrodinger equation for electron from this side, right? So then we know your potential is here, 0, right? So, but when you come here, your potential has this potential value. Again here, your potential is 0. You can solve your Schrodinger equation in these 3 regions and use the boundary conditions. Then you can get your tunneling coefficient. What is tunneling coefficient? What is this amplitude and probability and this one ratio, right? If you do that one, you get here we know it is decaying, right? So you have oscillations from this side, and these are fundamental here you have this one, then here it's going to decay, then again you have this sinusoidal. So anybody remember this function, how it looks like?
E to the minus
Minus
x.
beta, yeah, E minus beta times this distance, right? So this is what important for this, actually this is 2 times. So you can see all these things here, so that we know how K and everything, right? So what we need is this current actually is a function of that, this function, this 2 beta d. So the function that has a, this one have this potential and everything. E is related to the voltage. You can do all these things. So that. So you can see important thing is the 2 wave functions, they interact with each other, right? From the sample and from the tape. That's where the, so this is something. So that you can see, this is a nice diagram actually. These are the atoms, but what we need is these electrons, right? From that's why you need to have metal. STM you cannot use for insulated samples. That's one drawback of STM. You can only do when they are good conducting samples. It has to be metals, right? So, but if you want to scan something like DNA molecule or something, so they are not conducting, you cannot do STM. That's where the AFM is coming, right? So this only works for, you need to have enough tunneling. These are the electrons from each atom, right? So this is, electrons are the ones they are going to tunnel through, right? So that's why we get that nanoampere current. Oh, here now the piezoelectric effect, what I was talking, that's what makes that your tip move up and down, right? Why it is moving up and down? To keep that current constant. So when you do this one, you need to be careful because since we are doing this, mostly important is the z direction movement, right? XY direction also important, but that's why we need to have this something called this we call this piezoelectric coefficient. So that's actually a tensor. So you can have different components like 1, 1, 1, 2, 1, 3 like that. So here I'm talking about some in the elongation perpendicular to the E field or potential. So I am applying, suppose I have this one length L. If I apply electric field here, so the piezoelectric, what we need is elongating perpendicular to this E direction. So that means the initial this one, now it becomes is elongated by delta L. So we usually define that one as this the piezoelectric coefficient 3,1 or 1,3 whatever. Yeah. Usually this is defined as this how much it change delta L. Then there's a ratio of initial one per this electric field. So that's why delta L is given as L times E times D31. So for us, this is what important to move that C direction movement, right? So that's why you need to find this material that has good piezoelectric response. Anybody knows good piezoelectric material? Zinc oxide is a good one. So most, I think, the state-of-the-art material is PCT. It's a lead, zinc, titanium or something. Yeah, titanium. Lead, so not zinc. This is lead, zirconium, titanium. This is the known best piezoelectric material. For any commercial application, PCT is what we use. The zinc oxide also pretty nice. So, but I think this has higher, something called the figure of merit. So that means it will, if I apply some electric field or voltage, it will have more that delta L change, right? That's what we need. So this, you can see here for this L equals 1, for if I apply 380 volts per millimeter, that is the potential of the electric field, you get about 1 micrometer elongation. That's pretty good, right? So it's not a really huge voltage. That's what you need to have this control. So yeah, that's what that delta means. So here you can see the delta C value, that is actually delta L, right? Yeah, I wrote here, delta L value would be, delta L will be L times D31 times EL, right? EL means potential difference, gradient, that is V over that H. H is the height of the sample, that is this one. Okay. So, you have to do in there. So sometimes people use this 3 different material, like it has this the shape of XYZ, or sometimes people use simple cylinder. That's also fine, right? Okay, this feedback regulator means is did I talk about the PID control? Yeah, we did, right? When we talk about the temperature control, proportional integration and differentiation, right? So the similar thing happens here. If I have, because what you are measuring is this the tunneling current, right? So but we are trying to keep this tunneling current constant. So how do we do that in the feedback mechanism? You just have some constant reference I0, then you, if something changes, it will provide, so that is I, to with respect to this one, it will try to keep that I0 0 by changing your this proportional signal. So, or it can have some integral one. So eventually what you try is, if I have some current, if it tries to change, it will change this PID controls to keep the current constant. That's a basic electronic circuit. It's very typical for any, you can see how do they keep the I constant, right? So by changing this PID parameters. So in engineering, this is called the control systems, right? So basically, so this is the vibrating systems. So you have to vibration isolation. So typically, this is your STM, right? You have the tip sample here. So this is the body of the STM. If you keep it on a table like this, so you have to make sure you have some springs or like some rubber, something hold it. Basically, it will isolate these table oscillations through this damping, right? So this is what we are planning to do, right? These vibrations we are going to make it zero, right? Vibration zero. So that's why you have to make sure this something called this the resonance conditions. So you need to make sure they are not interfering with other resonances. So typically these things, either put it in some good vibration free table or just use some springs and things like that to hold it. So that's a little bit mechanical engineering kind of thing, right? But this is very important how to isolate the vibrations. Okay, so next one is the atomic force microscope. So actually something is missing here. So the same thing, you have the sample here, but now we have this cantilever. So still, I think something just this should be connected here. Same thing here. You have the same feedback, the negative feedback regulators, and apply voltage. And but only difference is now it is not the tunneling current you are measuring. in this case, what you are measuring is basically, you have some laser beam at this point. So then when it is scanning, so when it goes up and down, so this cantilever is going to bend, right? So when it bends, if you have some laser beam reflected off this one, you will see how that laser spot is going to move, right? Then we are going to put kind of some detector, so that has these different segments here. Suppose if you use a silicon diode or gallium arsenide diode or some photo detector. So then this the laser scan, so that will move this way or this way, right? So just imagine if this is the one, if this tip is bending like this, then you will see mostly reflected beam moving in this direction, right? If something happens like torsion or something like this, what will happen to the beam? It will mostly move this way, right? So then since you have these 4 different segments, you can get the signal from each, like this pixel kind of thing, right? So that will give you the image. That's pretty simple. Again, this is important how you have very sharp tip. Like I said, typically people use, these tips are made from silicon. Then also it has some resonance frequency. So you need to make sure, so when you buy this AFM tip, they will specify this is like 100 hertz peak or maybe 1 kilohertz resonance frequency tip. So you have to make sure what is that thing. So in this case, what we do is the piezo, again you have to use the piezoelectric material. In this case, basically, we are trying to keep the force kind of constant. So in the previous STM, you try to keep the current constant. In this one, because if you press on this one, so you have a force here, right? So, but that force, if you move to a different place, your force can be different. But feedback mechanism can make that force constant by moving it differently, right? Up and down or whatever. So then that force is very important because it can be just complete, we call the contact mode, or it can be some kind of tap-in mode or non-contact mode. There are 2 ways you can do this one. Actually, I have some details here. So these are typical how people do any deflections, right, from any beam. So STM, basically we are measuring how tunneling happens, right? So in this one, actually, we are looking at what happens when you have a laser beam reflected from your cantilever here. So if it moves, we know this is moving this way or that way. Or then another way to look at any deflection, how do you measure? Interferometer is pretty easy, right? So if you have some interference coming from maybe 2 beams, some interference pattern, if you bend this one, what will happen? The interference fringes will move, right? So we call the cone spiral and all these things coming. Even if you take like 2 glass slides, if you put these together and if you bend, what will happen? You will see nice interference patterns, right? It's this kind of shape, cone, so that interferometry is another way to look at the beam bending. Another one is you can measure the capacitance, right? If something changes, if you measure this one and this one, if something bends, the separation between the 2 is going to change. Then if you measure the capacitance, you can get that deflection, right? Because C is epsilon 0 over D, right? Simple term. If D is changing, your capacitance changes. That's one way to do this one. Another way to do is, actually we are doing right now something. We are trying to put some sample on something on the PET, that plastic material. We are going to bend it and see, apply some strain. So we get very nice results, but we don't know how much we are bending. So one way we are thinking about doing is put some, maybe some two dots or something. Then when you bend, you can see how much separation changes, right? From that you can get how much it is bending and things like that. So there are different ways people can do. Then you can measure the piezo resistance. So when there's a strain, right? That means your piezoelectric effect changes, so you can measure the voltage change or even the resistance. So there are many ways you can do this one. But in the AFM, usually people use this one here. So this is your cantilever. So this is the laser beam coming to this 4-segmented the photo detector. So whether it is bending this way or this way, you can see this laser beam is moving in this way or that way, right? So then each segment is responding differently, so then you can get information from that simultaneously. Like I said, this is a standard FM tip. You can buy these things. So actually they, like this size, right, it is very tiny. So each piece costs about maybe $10–15. These are typically silicon ones, but I don't know. In Louisville, there's a company called Noga Needles. So this Mehdi and his wife was my very first PhD student. So they opened a company here. So they are pretty good. So what they do is from the silicon, so they buy these silicon cantilevers. Then from there they grow very nice gallium oxide nanowires. So then they are much sharper, right? So then they can do much better imaging. So some people grow carbon nanotubes here. They are much smaller, right? Rather than this tip. This is pretty big tip actually. But if you can grow 1 nanometer tip, then you can do better imaging. So there are a lot of improvements happening here. So like I said here, whole thing is about measuring the pressure, right? So to keep the pressure constant. So, but they are bending. So the bending and all these things happen due to the, so then this piezoelectric movement will change that reflected laser beam, right? This is what there's something called this. Everybody knows, right? If you have two atoms coming together, what will happen? So when they come together, initially they are attractive, right? But when they come too close, what happens? So because then it is going to violate the what is called the Pauli exclusion principle, right? So then it becomes repulsive. So that's what here, right? So attractive force means up to, that is negative, right? Is attractive for longer distances. For closer distance, it is repulsive positive, right? If you take the sum of these two, they will look like this one there. So this is the equilibrium separation, right? So we know, so if you get, so one is a potential energy, one is the force. We know force is given by simply minus du by negative du over dx, right? So, but they both have the same shape. You can see, so here this is repulsive, this is attractive, but we are looking at very close, right? So the AFM can work either in this range, that means they are really in contact, right? So that is the contact mode, or you can do that a little bit farther, but still you need to make it move. So this is more like we call the tapping mode. So it's more, in this case it is completely in contact, but in this case they are, because they are attractive, right? So they are tapping mode. So depending on the sample, if you have a really fragile sample, this is not a good thing to do, right? You can demoid the sample. In that case, it's better to work on the tapping mode or non-contact mode. So that depending on what you like, you can do that. Yeah, that's pretty much what I want to talk about this one. So then, like I said, since these are tuning forks, right? They have their own natural frequencies. So, then how so you can see two different images. One image is something called these quantum corals, right? So these are actually individual atoms here doing the STM. So this, you can see the individual atom. Actually, people can even move atoms using the STM. I don't know whether you have seen people put atoms like this, I, B, M, like this. IBM people, they use the STM to move atoms to make this IBM letter. So you can see, so this is a picture of AFM, this is a DNA molecule. So biomolecules, because you cannot use STM to do this one, right? Because they are not conducting. But AFM can be used even for metallic samples, right? But STM has better resolution because you can easily see the atoms. So here is another comparison. So this is actually, remember I talk about TEM, we can do something called the scanning tunneling electron microscope. That's another way to look at the atoms. Here you can see individual atoms. So you can see individual atoms from STEM in the TEM and the scanning tunneling microscopy. These two are the ones you can easily do. Then there is something called the field emission microscope and things like that. Okay, so I will stop here and get back to the presentation. Any questions here?
Is that in the top right corner graphene?
What's that?
Was that graphene in the top right corner?
Oh, you mean that? Probably not. So these,
The hexagonal lattice?
so they are not really hexagonal, right? So if you look at the graphene, actually, there was a professor here. Right now I am working in his lab, Professor Usef. So he died like 5-6 years ago. He was an expert in this STM. He is one of the first people who imaged graphene. But that time, nobody knew about graphene. So he was very clever. He was making, just like, you know how graphene was invented, right? Doing this scotch tape thing. He used scotch tape to cleave graphene. That means you take graphite, you just put a cello tape and just take it out, right? So what Dr. Usef did was, then he imaged this on the graphite surface. Then he could see very nice graphene image. But that time nobody cared about graphene, right? So then people like Gaim and so those guys, what they did was, what they took from this end, they kept on going one by one and got into one individual graphene layer. But Dr. Usef, he already had, but that was not isolated. The graphene layer sitting on the graphite substrate. So it's more like, so he had graphite. So by cleaving this one, he had this graphene on this one. So he just imaged on this one and showed the graphene image. But when I came here, I had a discussion with him. So then, by that time already, people have discovered graphene, right? So what we did was, we just took some substrate and we put some mica sheet here, actually from here. Then we apply very large voltage. Then this graphene was just attracted to the substrate. So we could make graphene much easier way. But by that time, that group has already discovered. They did this scotch tape thing. But he is one of the first people who imaged this graphene, but he didn't know it's a freestanding graphene, right? So, but if you look at that one, what you are going to see is actually similar image, but you are going to see atoms like this. But you will see another this is coming from the one below that one, because you have, so this something called the AB stacking, right? You have atoms like this, because unless you have single graphene layer, you will see this hexagon, and also you will see the one from the layer below that one.
You remember my presentation? That's what it was there.
Okay, so let's do quickly this spectroscopy. So I'm going to talk about several spectroscopy techniques. So basically, start with the optical spectroscopy. That's the one we all do, right? So then go to even optical is Raman, IR spectroscopy. They all are. So then we'll do some electron, or even like electron emission spectroscopy, like photoelectron or X-ray emission, those kind of spectroscopy. Then eventually, so those are basically we are talking about. So when you talk about optical microscopy, it's all about Maxwell's equation, right? So these are the simple Maxwell's equation in vacuum, but in general we have, how do you change this one? Maybe this is important for you, or this one. Okay. So typically for any medium we have, this is not zero, right? So then this equation also, this is same, right? This is very general, the Faraday's law. This is also true. So this also has, anybody remember what is missing here?
The Maxwell equation, the 1 over c squared.
Yeah, mu 0 j, right?
Yeah.
You have, yeah, that's also, if you have this one,
Oh.
basically, that cross B is, you need to have this. Then you have epsilon 0, mu 0, dE over dt, right? This is basically the what is called the,
Yeah.
what do you call this one?
Displacement current.
Displacement current, yes. So, but in vacuum, you don't have any free electrons or free charges or free currents, right? That's why. So then we all know about the region of the spectrum going from cosmic waves to maybe large radio waves, right? Like kilometer range, large wavelengths or very small energies, or go to very small angstrom size wavelengths with very high energies, right? So then in between you have the visible range. You get this one. So then there are some of the how you make this different radiation, how you make the gamma radiation. Gamma radiation is coming from basically nuclear reaction, right? Some radioactivity. So others we can make by molecular excitation, so rotational, vibrational energy. All quantum mechanics, right? So we have different state. So then you have this NMR resonance. That's mostly the spin of the nuclei, right? I don't know whether you're familiar with MRI and EPR. NMR is nuclear magnetic resistance. That means the resonance. That's the spin of the nuclei, right? So protons and neutrons. So then EPR is basically electron spin resonance. So it's orbital electrons. So these are two different the spectroscopy thing. Then microwave absorption. How the microwave is, what is the origin of microwaves? They all coming from the molecular rotations, right? So if you take water molecule, right? So you know how water can absorb microwaves and how to produce, like used in the something called the so the others are all these transitions, right? So if you have from high energy level to low energy level, you get all these radiations coming out. So, inner electrons. These those things. Here are some. So then I think when you do the spectroscopy, nowadays everything is based on lasers, right? Because lasers have this nice coherence, right? So, but still you can do with broad light. So if you have a broad light, only thing you need is what? Just some dispersive element, right? So either prism or diffraction grating, then you can separate into different wavelengths, right? So that's called the dispersion, right? In the old spectrometers, we had prism to separate, but nowadays you have much higher resolving power with diffraction gratings, right? So everything is based on. Then all kind of lasers. Everybody familiar with the lasers, right? So something called the popular immersion. So then typically you excite something to higher energy level. So then what happens? So they basically relax to the low energy level, right? So then it emits some the radiation. So then this radiation can, so the problem is there's something called the population inversion. So typically electrons like to stay in the lower level, right? Population inversion means you have more electrons in the higher energy state, right? So then when these emission, they are coming, so they can promote further emission. We call the stimulated emission, right? So that's why you get more and more stimulated. That's where the resonance, the things come in. So then there are different kind of lasers. Solid state lasers, they are easy, right? This basically PN junctions, right? So then we have to have the right condition. So typically YAG lasers, they are emitting like 1064 nanometers. So then gas lasers, that's the most common one. If you see like this red wave, the red color big laser, they are all helium neon gas lasers, right? Because of these two gases, they have different energy states, so they can have something called the interatomic collisions. From the helium side, it can excite something in the neon, so they emit the laser light. Excimer lasers, they are basically, they use some kind of dimers. They can be like fluorine or chlorine, so in gases mixed with some inert gas. So these are pretty difficult because you have to have these different gases pumped into the system. Dye lasers, they are even more difficult because they have to use these complex dyes sometimes in the liquid solutions, right? So they are not very easy to use. So semiconductor lasers, they are the easiest one to use, but they don't have very high power. So I think excimer lasers, they are mostly like UV kind of lasers. They have very high power. So actually his uncle, he's one of the, I think, pioneers in this excimer lasers. He's working in a company, they produce with high power excimer lasers. So they are basically the UV light. So now they are pushing it to like deep UV. So that means your wavelengths are even smaller, right? So they are going to use them for this more this microfabrication kind of thing because they have much narrower. Because electron beams are really good, but electron beams are not very easy to do. But if you have deep UV excimer lasers, they have much more higher potential to work on these things. Then there are something called free electron lasers. There you have to go to these centers, like if you go to Virginia, so they have this free electron like large laser facilities. Nobody has that one in a lab. They are like a user facility. So yeah, this is typically what I was talking about. So this is helium neon laser. You can see helium atom has this 1s, 2s states. So with some excitation, you can go to higher state, right? So then inside these two atoms collision, so that this energy can be transferred to the neon atom. So then they will have emission from here 3s to 2p here. Then it emits this 632. Typical helium neon laser is red color, right? So it's moving this 632 nanometer. So typically in laser, what you have is once you make this like stimulated emission, right? So you have this many photons are coming out, then they are in a kind of, we call it some cavity. So there's two mirrors. One mirror is perfectly reflective mirror. So then you get, every time when it reflects back and forth, there's again medium. So it gets more energy. So eventually it becomes really intense and passes through the this opening here. So you have these two mirrors here. That's standard. I think I'm not going to talk about the lasers, right? We are going to use lasers for the spectroscopy. That's all. So why do we use lasers? If you take typical any light source, we know they are not very coherent, right? But if you take, sorry, here, so that is for the laser. If you take from any light source, they are very incoherent, right? Spatially, they are not coherent. So you can see when this is maximum, this can be minimum. But if you take laser, they are very coherent. Coherent means every photon, when one has maximum, other one also has maximum, right? They are coherent. So that's why. So they have very long coherent length, both spatially and temporally, time and space. So that's why we like to use. So you can see how, if you look at the intensity, you have just one single peak, right? For the laser, so narrow, very sharp. If you take a light, what you get is a broad one, right? It's a many wavelengths. But that's important if you want to use for different color response, right? You use a broad light, then separate each color and see how they look through the sample. So then electron source, we talk about these things, right? So how field emission and thermionic emission. So this is your material. So this is the Fermi energy. So this is the vacuum level. You can see when you apply voltage, this line becomes like this one, EDX. So then you can see your total barrier becomes like this. So then you can have, this is we call the field emission. This is we call going from here to here, that's the thermionic emission. Then you can have something in between called the thermionic field emission. That's what we use typically for electron beam. I think we discussed about this one. Yeah, view particle. I think this is another important thing. If you look at any spectral response, different spectra, always your x-axis is energy, right? So this energy has many different units. That's something like, if you are looking at some maybe UV light or something, typically they give this one in terms of electron volts. So it can be electron volts. Then also, since these are photons, right? Photons is basically h nu. So this means h c over lambda, right? So sometimes this your x-axis can be hertz because that nu is hertz, right? So sometimes it can be 1 over lambda. That means it can be centimeter inverse. So that's what's your Raman, right? Raman, what is the unit? Typically it is centimeter inverse because that is 1 over lambda, right? So these are different units, so you should know a little bit about what. So this is a very important thing. 1 electron volt is like 1.23 micrometers. So this is a very, something everybody should know. So if you talk about 1 electron volt in terms of because that corresponds to some length, right? So that length is 1.23 micrometer. This is a very important unit for anybody to remember. But they all are, you can either write as electron volt or by hertz or 1 over lambda, any unit. Please remember that one. So, but if you say centimeter inverse, it's really energy unit, right? It's 1 over lambda. So these are the processes we talk about. This one, yeah, this is important. Like if you have something, so typically, so you can have this some excited state, right? So if you have excitation from very large energy to your ground state, you usually, actually this is like not emission, it's absorption. So if you have ultraviolet, it can excite it to much higher, right? Because large energy. If you have visible, so it can excite to here. Infrared, so they are low energy, right? So but they are in the region of like molecular vibration. So even the lower energies, so they are more like rotation and vibration. I'll talk about all these things. So please read these things. So this is what we talk about the dispersion, right? If you have broadband, how you, so this one to break into different, so this coming one broad one, so you can separate into violet to red, right? So, but you can do this way, or you can do ND sin theta equals D sin theta equals n lambda, right? So for grating equation, refraction grating. So this one, this is how from the prism it is changing, right? Delta is given by A sin A plus D over 2 divided by sin A over 2. Depending on this D, you can get different deviations, right? For diffraction grating, basically it is D sin theta equals n lambda. For different lambda, you have different theta, right? So you get this. You can have positive and negative. That's what we do in the typical something called a UV vis. Have you heard about that word? UV vis spectrometer. That's the most general spectrometer. If you want to study some material, first thing you do is just go to that UV vis. That UV vis means ultraviolet down to the visible light. So you can scan. You have two sources. You can have like tungsten bulb and some another, I cannot remember. So they will give you the entire the broadband light. So use the spectrometer, what is the gradient to separate into different colors. So there is another one everybody should remember, something called this energy dispersive principle. So typically, how do you see whether you have some signal? So when you excite something, you will get signal coming out of that, right? Then we are going to have some detector to separate those, find what are those things. When you do that one, we call this dispersive technique. What they do is they define high and low levels. So only the signal that is between these two are counted as some signal. If it is above this one or below this one, you don't count it. So like if you take something like this, if you, as a function of time, if you do like this is the lower limit, this is the upper limit. Anything below this one is not counted. So anything above this one also not counted. That means it's only counting this region, right? So because here you can see this is above this. So here they are, so this is not counted. But in this region, this is the only region they are in between, right? Then you say this one as your signal. So that's the energy dispersive principle. So you define your two limits, upper and, so this is more like clipping circuit in electronics. You remember, clipping means you define the, so if you have something like this, you just clip this one only. This, if you use something called this Zener diode, so you get this kind of, it is a clipping, the top and bottom. So anything, this one will be count one. If you have another signal like this one, then I have another signal coming like that. That's how typically you, this is an important thing to know, dispersive technique. Okay, so this I think basic things everybody knows this one. Okay, so this is how the simple UV spectrometer works, very simple, even anybody can make this spectrometer, very simple. So only thing you need is simple photo detector. So that you can buy from Thor Lab, maybe $15. So then you need a simple broad light source, right? So then you have the lens to focus here. So this is the spectrometer. So this will be really expensive, right? But what you have inside the spectrometer is very simple. You have one mirror here, then you have grating here, there's another mirror, that's it. So then this light, this can be broad light, right? So it's like a tungsten lamp or anything. You just focus it to this, this is the entrance of your spectrometer. So then what happens? So this is getting reflected from your from the mirror. So then from here they are getting dispersed, right? So different colors. So then after this one, you can put your sample anywhere here, right? So then you can get if suppose if I keep my sample here. So then when it is going through here, you can have absorption or whatever, right? So then you can see what is happening inside here. So this is what we call the spectrometer. So actually, ideally it would be good if you can put your sample somewhere here. Yeah, I think this is, this could be your sample. So then it's already going through this one, and it can be any place you want to have here. So basically you need to have like two reflections and the grating. Grating is to separate the lambda. So then what you are going to see is when you connect to this photomultiplier tube or photodiode. So basically you have this different lambda because that's coming from this one, right? So you can separate this one, then look at this signal coming from the photodiode. So depending on your sample is absorbed in something, then you will see this absorption, right? So maybe actually absorption, if you have, that's going to decrease, right? So you have some, if you look at the absorption, so you have some signal, so at some wavelength, you will see something, right? Because that's absorbed. So then you have something. So depending on your sample is absorbed in different wavelengths, you will see this spectrum here. So either you can have absorption or you can measure transmission. If your sample is transparent, so you can look at how much light is coming outside. But sometimes your sample can be very thick. Then how do you do that? Then your light is not passing through, right? So then there's some special attachment called the diffuse reflection. So you have to take the reflected light. So here I am talking about something passing through, right? So for this to happen, your sample should be thin enough, right? Or it should be on a transparent medium. But if you are putting your sample on say some metal foil or something, right? Light cannot go through that. In that case, you need to get the reflected beam. So reflected beam can have information like this. So we call this is a monochromator because this has one diffraction gradient, right? So there are some spectrometers, they have more than one diffraction gradients. So they call a double monochromator. So they have better resolution. Okay? So this is what I was talking about. Transmittance is what initial, with respect to the initial power, how much is passing through, right? That is the transmission. Then absorption is usually the inverse of that one, right? Transmittance. So typically they define as 1/T, but they take the logarithmic of that one. So actually, ideally, this is what you have, right? So if you have light coming, there are few things can happen. This is incoming light. Then you can have reflection, right? So then you can have absorption here, and you can have transmission. All these things can happen, right? So if you typically you can write it as reflection plus absorption plus transmission. They all are like, if you take everything, they are more like one, right? So then that's why they typically, if you neglect this one, you can work on this relationship. That's, I think, close enough. Sometimes we define this one as optical density. So next I want to talk a little bit about the polarization. So everybody familiar with the polarization? So polarization means your EM wave, what is the direction of electric field, right? So most of like the lasers, if you take, they are polarized. So they can be in the horizontal or vertical. We call P polarized, that means your electric field is in the plane of the incidence. Or so then there's S polarization, that means that is perpendicular to the head. Yeah, this SOP polarization. So P means this is the incidence plane. So if your electric field vector is here, this one, right? Yeah. So this is in the plane of the incidence. We call that the P polarized. So that means if you this is the light, your electric field is on this plane. So, or if your electric field is on this plane, we call it the S polarized. So when you first talk about, you need to know whether it's S polarized or P polarized. So then I think everybody should know about wave plates. So anybody familiar with everybody knows a polarizer, right? What is polarizer? It has something called this polarization axis. So this always that when it passes through, the outcoming wave is in the direction of that polarization axis, right? So even if you have unpolarized light, suppose this is my unpolarized light, that means the electric field is in every direction, right? If I pass through a polarizer has something called the optic axis, right? So when it passes through, what happens? Only the E vector in this direction will pass through, right? So this way we can get whatever you want. So then this polarization you can control. This is linearly polarized, right? If I want to change this polarization direction, what can we do?
You can change the phase shift.
Yeah, so there's something called the half wave plates. Half wave plate can change this polarization direction anywhere you want. So I will explain how it happens. So then there's something called this is half wave plate, means lambda over 2. That means, so typically, you know how phase and path length changes, right? So typically 2 pi over lambda times, this one gives you the phase difference. This means actually pi. You have pi phase change when you have half wave plate. If you have quarter wave plate, this means you have 2 pi over lambda times this lambda over 4. That means you have pi over 2, 90-degree phase change. So actually this phase change is coming from, I don't know whether you are familiar with, there's something called the ordinary wave and the extraordinary wave, right? So that difference, that's the bifringence. So depending on that difference, you get this one. So basically, if I have this is polarized light. If I have a half wave plate, I can change the direction of my polarization. So, but we can change this polarization direction and move it any direction you want. That's what we are doing right now. So our Raman system, it had only one polarization. So now we set up something we can do. This something called the polarized Raman. That means we can change this polarization and see how the Raman spectrum changes with that one. So if you have a quarter wave plate, you can make the linear polarized light into like circularly polarized or even elliptically polarized. So, you know, the linear polarized, you have the same magnitude, right? But if you have circular polarized, when it comes, they are kind of not completing that one, right? So it's pretty much, so then still your, this two direction, they have the same height, but if they are different, then it becomes elliptically polarized, right? So those things you have to do. But right now, just remember, half wave plane, they are like pi degree, so then you can change the polarization direction. If you have quarter wave plane, that means 90 degrees, right? So that they can make your linearly polarized light into circularly polarized or even elliptically polarized. This graph will give you good one about, so this is the phase change, right? 2 pi over lambda time. This is what I said, the refractive index for these two waves, something called the ordinary wave and the extraordinary wave. The difference between those two, these are the bi-3 fringes, right? So that will tell you how things change. So if you look at this one, if you want to take the exponential of that one, you can see when they are 0, this becomes 1. If this pi by 2, this becomes I. So pi by 2 means this one, that is quarter wave rate, right? Then this becomes, if this is plus I, this is left circularly polarized. If this is 3 pi by over 2, this is minus I, that is right circularly polarized. If it is pi, this is basically half wave plate, then this becomes simply changing by this 45 degree, the linear polarized. Half wave plate is just to change the direction of the polarization of the linearly polarized one. Quarter wave plate is if you want to change from linear to circular elliptical polarization. Please read this one, this will be here. This is important. Quarter wave plate creates a circular polarization. Half wave plate creates linear polarization, but depending on plus 45 and minus 45. If you can really tilt yourself. If I had this polarization, if I want like different directions, what I do is take a half wave plate, right? And just nowadays you can just rotate that direction and make this one any angle you want. That's what we are doing right now. So molecular vibrations. Almost like. So yeah, so this is what I want to mostly talk about. So if you have different atoms, so how they are going to, few things can happen, right? If you have two molecules, they can think about attached by a spring, right? They can oscillate. So then if you have like something like 3 atoms, so then they also can oscillate, then also they can rotate, right? So even this one can also rotate about this axis, right? So that's what the rotational, so you can have vibrational mode, then it can have rotational mode. So they all are quantum mechanical effects. So they all are quantized levels. So then, yeah, you can see all these things. Then when this happens, you have different things happening. So first I am going to talk about a little bit about Raman scattering. Raman scattering is really a simple experiment. So, but that is actually, if you look at Raman scattering, they are really weak signals, right? So if you have some light coming here, so then we have sample here. So let me see that like this here. So this is some laser coming from, say, h-nu frequency. So then this is getting reflected. So that's an elastic reflection, right? But there are some inelastic scattering. So that will give you this Raman scattered light. They are very weak. So these are inelastic scattering, right? So then we are going to collect this one to my spectrometer, right? So this is happening. So actually this one will have, so since this one go with the same frequency, right? So that's it. But this one will give with the reduced frequency. So that's the one we are going to collect from my monochromator. That's where I have all this. Spectrometer is what? You have these mirrors and the grating, right? That's all. So then you can look at what's the value of that one. So that's all. The Raman spectrometer is laser. Come in here. Look at this. Inelastically scattered light. So this is more like the Rayleigh scattered light. That means your energy doesn't change. We don't want that one. So that doesn't tell anything about the sample. What you need to know is, what is that? Inelastically scattered light. So this is very small amount compared to elastically scattered light. So that's why I think it's a very weak signal. Yeah.
Is this some like 1 in 10 million photons?
Yes,
or-
exactly. Yeah. So there are millions. Yeah, that's small. So then you can look at by this one. You can look at different kind of vibrations, right? So you have the scissor mode or this different modes. So but basically what you are doing is you have h nu come in, then h nu prime leave in, right? So then what you are measuring is something called the Raman shift. That means this h nu minus h nu prime. That's what you are measuring, right? So this means h c 1 over lambda minus lambda c. This is what you are measuring. That is in centimeter inverse. So we know this lambda 0, right? What is that? So if I use a 632 nanometer, that is that value. So what you are measuring is this delta 1. If you write this one, lambda 0, lambda 0 minus lambda. This is what you are measuring as the Raman shift. So we'll talk about different things. Yeah. So I think this is almost time. Yeah. So I'll talk about from here. So I think Thursday I will finish the spectrometer thing. So then Tuesday to talk all about the microfabrication, like clean room techniques we use, how to do the lithography and things like that. Then Thursday you guys are going to teach me. Right?
What time
Yeah.
are we meeting on next Thursday?
Yeah, next Thursday.
What time?
Right here.
We're gonna meet a little early so we get out.
Yeah, let's do a little earlier. So how about 5 o'clock? 5? Everybody's fine, 5 o'clock? Yeah, then we can go home at the same time, right? Yeah. Yeah, don't over prepare, so just, yeah. So don't waste too much time, that's what I'm telling you. So I think you guys will be still busy until this Saturday, right? After Saturday, we'll have time to do this.
Then they'll be busy in a different way,
Different, exactly. Yeah.
playing catch up.
Yeah. So, you and I can meet maybe tomorrow sometimes, Sam?
Yeah, I'll be free in the afternoon.
Afternoon, yeah, that's fine with me, yeah.
I'm available
So I teach
between
until,
1 to
yeah.
4.
Yeah, that's fine. I teach until 11.
Okay,
After that, 1 o'clock, let's meet.
1 o'clock.
Let's meet in the lab.
Okay. I think I said what my presentation was,
Yeah,
but I was just gonna do the CVD
Yeah,
and the
yeah.
plasma enhanced
Yeah,
CVD.
yeah, yeah.
So-
If you want, because I'm not planning to do, I had another set of lectures for
For the
nanofabrication. If
Okay.
you want, I can send that one. Different techniques how to do nanomaterial.
Okay.
But this time I don't have time to do that one. I can send you that. Yeah, you can use something from that.
Okay.
Yeah, yeah. You two just let me know what you want. try something simple that is going to clear.